Hi, I'm Toby. I'm the Emiquon project coordinator here at the Illinois River Biological Station. So I'm out on the preserve monitoring the fisheries population and the aquatic vegetation population as part of the work that I do here. Our question for today is whether common carp have driven the loss of aquatic submerged vegetation at Emiquon, or if they're preventing the recovery of these populations. Before we get started, I'd like to thank all of the people who are involved. First, the Nature Conservancy and Illinois River Biological Station for funding data from both of those places and also from Forbes, along with some materials from all these sources. I'd like to thank Sally, Doug, Maria, and Randy for all of their support, Jim and Levi for their support, staff all around the field station, and all the technicians that are always doing a lot of the heavy lifting when we're going out in the field. And I'd like to thank previous Emiquon coordinators, Ali and Amber, for staying in touch and helping me get oriented to the task as I come on here in the past couple of years. So just as a reminder from last year and just looking at the data, submerged aquatic vegetation has declined in Emiquon over the past 5 or so years. Our question today is, are common carp to blame? Submerged aquatic vegetation declined, but for the first decade, it had a pretty healthy start. Without a lot of encouragement, apart from flooding the preserve, submerged aquatic vegetation took off with lots of healthy native communities in very strong abundances, covering a lot of the preserve. However, in the last 5 years, there have been declines. Here we can see declines in areal extent represented by cover maps produced by Forbes, and this dark blue area in most of 2017 and 2019 has declined and been replaced by open water light blue and by essentially land in the light tan color. We can also see that where the vegetation exists, it follows a similar pattern in declining in 2018 when the water was low, and in 2020 and 21. This is the abundance of vegetation at those sites, not the actual total coverage throughout the preserve. So the vegetation is really declining. Recently, we've also had continued low levels. The vegetation is not recovering. And there's enough water out there, especially in the open water areas in the middle, in areas that have recently supported SAV, but don't currently. So that's a matter for concern. Here's an example of a nearshore area on the main lake that would have once supported submerged aquatic vegetation, and all we see is a patch of willows near the shore. Here's another example in the middle of Flag Lake where this would have been densely filled with submerged aquatic vegetation even in 2019, but in the last few years, it's a pretty open landscape. Where there is vegetation in those shallow areas, a lot of the times it's a lotus community with a mix of some duckweed. That said, we are seeing some beds of vegetation. This is a bed of mostly native milfoil in northern Flag Lake. This is a community of American pondweed and sago and some naiads up in the very northern reaches of Flag Lake as well. So our question is, what's causing these declines? One of the top hypotheses is common carp abundances, because they've been known to disturb aquatic vegetation in other habitats. Another major competitor is simple turbidity increases. We've seen this in the lake, and obviously it has an impact on aquatic vegetation. Herbivory from swans is another possibility, and we've also considered the possibility of hydrology and low water levels. That said, all of these factors do work together, but one of the most compelling is common carp abundances. Our question is, are there enough common carp to negatively impact the aquatic vegetation at Emiquon? So to start this, we need to look at what we know about the levels of common carp that will affect the aquatic vegetation. So a paper by Crivelli in 1983, in which he also references a paper by Roble in 1961, looked at percent loss of aquatic vegetation in one season as a result of certain kilograms per area of common carp. And they saw 10% loss of that vegetation with 100 kilograms per hectare, 20 to 40% loss with 300 to 400 kilograms per hectare, and 50% loss at over 450 to 500 kilograms per hectare. More recently, Bayer et al. Has, in looking at Hennepin and Hopper lakes, has shown quicker declines at lower biomass levels, including 20% loss at less than 50 kilograms per hectare, 40% loss at 100 kilograms per hectare, and 80% loss at just 250 kilograms per hectare. It seems like Hennepin Hopper is a closer system that is more like Emiquon and is probably more relevant for the system that we are looking at here. In terms of estimating the abundance of common carp at Emiquon, the main data source that we have is the monitoring data, and one of the more well-trusted sources of data is our electrofishing data. Of course, that's not directly an abundance effort, but thankfully, folks like Bayer and Sorensen in their 2012 paper, as we've had them with us today, have a conversion to take carp per hour electrofishing and convert it into carp per hectare. Of course, the data looks the same, but the y-axis has changed. And using the average weight at each of these years for carp, I'm also able to take this and turn that into a kilogram per hectare. And so this gives us a basis from which to consider whether our carp are at sufficiently high levels to be degrading our SAV. Using this highest level here, 100 kilograms per hectare, that was observed in 2018 when the water was low and the carp might have been quite concentrated, and which would give us the most chances of saying that the carp might actually be affecting the system. We can compare what expected loss of SAV would be based on the older papers by Crivelli and Roble, which is 10% loss, or by the more recent and local paper at Hennepin Hopper, which would be 40% loss. Using a different approach, a lot of effort was put into collecting carp in 2019, carp of all types, and late in the year, in October, a lot of carp were marked. Common carp were not the main focus of this, but 187 common carp were collected and marked in October of 2019. There were only 4 recaptures that have been noted, and they were all from 2020, and they spanned April through December. I wasn't really sure what to make the main total amount captured time frame be, so I just included the whole year in which those recaptures were made, and that happens to be the following year, so it seems to be a somewhat reasonable starting point for getting some kind of an estimate of abundance. These numbers are rather shaky for just all of the assumptions that are going in. It's possible also that some marked fish were missed, but it's what we have to go on, so we'll see what we get. This yields a carp abundance of 50,000 in the whole system. Assuming 780 acres, which is based on the water area at the time of the sampling, the first sampling, and some of the aquatic vegetation area as well, this would result in 63 carp per hectare. Because the carp that were caught using these methods weighed an average of 12 pounds or 5.5 kilograms, this results in about 350 kilograms per hectare of carp with an error of about 140. Therefore, based on Crivelli and Roble, we might expect at least 50% loss in SAV. And based on Bayer et al. Related to Hennepin and Hopper, we would expect more than 80% loss of SAV. These are high numbers and significant. The takeaway from this is that common carp are likely to be having a significant impact on the aquatic vegetation at Emiquon. The main reason we would not say this for sure is just a question about how reliable our population estimates are, converting CPUE to an abundance or using the one mark recapture event that we have, in which we had very few recaptures. While we were looking at the use of catch per unit effort to estimate abundance of carp in the preserve, one of the things we were able to see was an increase over time out of our data. However, this began to be questionable given the relationship between the abundance of carp and water level. Comparing each of the sampling events shown on the previous graph to its water surface area, the catch per unit effort of common carp increases with lower water surface area, implying that carp get more concentrated, which makes sense. However, since lower water levels have been more common in recent years, we wondered if this might artificially be increasing the trend over time that we see in our data. We ran another analysis comparing catch per unit effort to the time and also to the water levels. We found that both factors were highly significant. So carp are increasing over time, and there is an effect of water surface area. Interestingly, the later in time that you look, the more a negative relationship exists between catch per unit effort of carp and the water surface area. And that's, I guess, what I tried to show in this plot of 3 representative years, showing how the slope becomes more negative as time goes on. I really wouldn't put too much stock in any of the actual values on the prediction. Here we can see the same plot that we started with the significant increase over time in catch per unit effort of carp. And then overlaid onto this, we will see what the model expects the catch per unit effort of carp to be through that time series, accounting both for the increase over time, but also the changing water levels that are being experienced throughout the preserve. And it's interesting to note that this seems to map fairly consistently with the data points shown on the plot. And this thick black line is probably somewhat indicative of the concentration of carp, which may be the more important factor when it comes to the effect on submerged aquatic vegetation. Also interesting to plot here is if we hold the water level at a consistent value and then tell the model to predict what the catch per unit effort should be across time, we see an increasing trend. Again, this is just another way of illustrating that the model shows a significant increase over time in catch per unit effort, even when we account for water levels. While it seems like we have lots of carp in Emiquon, it's true that there are inherent uncertainties with the use of catch per unit effort and converting it to a kilogram per hectare value. And it's also true that we only got 4 recaptures in the one recapture event that was done. And so perhaps it's time for some more mark recapture if we need higher certainty. Or perhaps there's just a whole lot of carp out there. Of course, as mentioned earlier in the presentation, there are some other possible reasons for declines in SAV. Probably the top candidate for alternative explanations to carp is simply an increase in turbidity or decrease in water clarity. On the right, you can see a picture of North Flag Lake with very chocolate milk water, where there used to be abundant submerged aquatic vegetation. Now, there are scattered patches of invasive milfoil hanging on for dear life. If turbidity is to blame, it may have come about because of dropped water levels that kicked up some sediments that were softer towards the middle of the lake, which would explain increases in turbidity concomitant with declines in water levels. It also could be a result of the natural succession of the lake and sedimentation processes continuing to occur. It could also be keeping the aquatic vegetation from rebounding, simply because now that the aquatic vegetation has been lost for whatever reason, the loss of that hold fast on the sediments is allowing it to be stirred up with every storm event, especially in a large, shallow lake. And of course, one of the causes of turbidity is carp populations themselves, which we can't rule out the effects of that. Just showing some of the data, on the bottom left we have Secchi stick mean depth over the years. Obviously it's declines over time. You can see significant decline in 2018 and also since 2021. In the upper right, there's a plot showing turbidity values where we found vegetation and even where we didn't. And note that where we found vegetation would include this picture just below where there's sparse milfoil beds in chocolate milk water. There is higher turbidity where there are plants, but this is also important to recognize that this is shallower water. When taking those water clarity values and dividing them by the depth of the water, we can see in the upper right corner that vegetation does exist where the light can get deeper compared to the bottom. So if the light's getting 25 to 50% of the way down, that's much better for the vegetation, and that's where they're going to hang out, even if it's this chocolate milk water with these sparse milfoil beds. On the lower left, we can see that the average values for this observed at least fish sampling sites over the years has declined from the top distribution plot down to the bottom, with the distribution shifting to the left as time has gone on. Of course, lowering water levels reduces the available habitat for aquatic vegetation, but it can also potentially have a role in increasing turbidity. It may concentrate common carp, which also may increase turbidity or uproot plants. Here we can see the hydrograph, and we can see the biomass of SAV plots, and we can see a comparison of the years in which water was low being associated with the years in which vegetation was also low. In terms of what we're going to do going forward, one of the things we want to answer is whether turbidity could be driven by wind, and whether that wind fetch and unvegetated area could be one of the things getting in the way of recovery. It's hard to do that when we're not out there all the time, especially during the really windy events that are super choppy, and it's also somewhat hard to measure turbidity in the shallower areas where we take our airboat without the airboat disturbing the sediments too much. So we're going to be employing the National Great Rivers Research and Education Center's Grion buoy. Thanks to Sarah for helping arrange that and hopefully getting at that question.